And in these cases, you don't use the logs affected by those cavities. Neutron density are affected by bed hole or these cavities in the hole. And the bed hole, it's measured with the caliper. As Rauf explained before, you have the caliper, which has a lot of arm and open and calculate for you a caliper. If is it one, it will calculate one caliper. If is it a lot, it will calculate multiple and will calculate an average. For simplicity, I am displaying the average caliper, and you can see when we enter the reservoir, the caliper is straight line, 8.5 inch, which is the hole size. But at the shale section, the caliper went very, very big. This is all bed holes, and that's why we don't use neutron density for the bed holes. And that's automatic in the software. So as a recap, always use multiple equation and multiple sources to estimate your component. Example here is the V-shale. After we are done with the V-shale, we go and calculate the porosity, okay? And the porosity, the main indicator for porosity One second. Brahim is asking me to record it. How can I record it, Mr. Brahim? Hello?
Khaled, there is a little button on the bottom here. Just click on it. You are co-host.
Yes.
Just click on record. Yeah, you started recording. You're good to go. You're good to go.
We started?
It's a start, yes.
Okay, sorry. We'll go back to the presentation. So after calculating the volume of shale, the second step is you calculate your porosity. And also, we try to keep it simple, okay? Calculation of porosity is mainly controlled by three logs: the density, the sonic, and the neutron, okay? So these three logs are the best porosity indicator, and some people, they call them porosity tools, okay? Those are the three main logs. We go one by one. So to calculate, because these guys, they don't give you porosity value. They give you a physical measurement, a neutron measurement, a density measurement, and acoustic velocity measurement. To calculate your porosity, you need to know what kind of rock you have. Lithology, is it quartz, is it limestone, is it shale, is it mixed? And also, you need to know what you have as a fluid inside the porosity. For simplicity, we start with a simple rock, 100% quartz with porosity filled with water. Simple, yeah? So when we understand that, we add to it shale, and after that, we add to it hydrocarbon. As I said, my advice for you yesterday, always start simple. Always start simple. Use an Excel and start simple. So for a bulk density for a rock with no shale, so simply the density is equal to the mixed densities of the two elements. So it's equal to the density of the matrix multiplied by the volume of the matrix. And the volume of the matrix, remember that in petrophysics, the whole volume is equal to 1. Okay? So the total volume is equal to 1. That makes the volume of matrix equal to 1 minus the porosity. That's the volume of the matrix. Multiplied by the density of the matrix plus the density of the liquid or fluid multiplied by the proportion of the liquid, which is the porosity. That's the density if we measure it in the lab, okay? So, some numbers here, if you have a quartz, the density is 2.65. If you have a limestone or calcite, it's 2.71. And if you have a dolomite, which is carbonate, the density is slightly heavier at 2.87. Now, you don't see for the fluid and depends what you have. If you have water, is around 1 based on the salinity. If you have oil, it is based on how deep, how the pressure and the composition is, and depends. between 0.8, 0.7 for lighter oil, up to 1 for very heavy oil. If you have gas, it's not very low at reservoir condition, because at reservoir condition, we have very, very high pressure. Usually the gas is between 0.2 to 0.3. And there is tools to calculate this values for you. Don't worry. Always, whenever you work for a company, those numbers are already studied and delivered, provided to you. For the shale is later on we talk about it. So if there is no shale and the porosity is filled with water, so the porosity calculation is very simple. You take the equation of rho B, reverse it around, and you will get your porosity. So your porosity is equal to the log, the density of the matrix minus the log value divided by the density of the matrix minus the density of the fluid. And if you look closely, this equation almost the same like a V shale from gamma ray. So if you understand the V shale from gamma ray is the same as porosity from density for clean rocks. So you see those equations, they come back to you again and again and again. It's very simple, straightforward. Now, let's say that we have a little bit of shale. So if we have a little bit of shale, the equation is the same. Okay, now the correction for shale is different from people to people, but most of the standard method of calculating porosity with shale, it will keep the same formula. The formula does not change, okay? It's rho matrix minus rho log divided by rho matrix minus rho fluid. It's the same. The only difference is the rho matrix now, it's not 2.65 anymore. We will adjust it to the volume of shale. So our rho matrix will be equal to the clean rho matrix minus V shale multiplied by rho matrix density minus density of the shale. So we adjust and correct the rho matrix, and it will give us porosity corrected to shale. Very easy to understand. Now, what is the density of the shale? The density, because we said the shale, it's not a stable, it's not a mineral, it's a rock. That's why it has a property changing from one asset to another asset. If you go, for example, in Algeria, if you go to Hassan Saud shale, is not the same as Elizi shale, is not the same as the shale above, the shale below, because it's a rock, it's a mix of stuff. Always the property of the shale, don't pick them from books, guys. Always go to your interval, look to the shale above or below the reservoir, and go and read the value from there. So you go to the density log in front of very thick shale and see the reading and take an average value. Okay, that's how you pick your V shale properties. So if we have hydrocarbon, so the porosity here now it has water and hydrocarbon. Okay, that's the equation that will include the fluid, the density of the fluid, which is the water in the nearby well section, and after that multiply plus the hydrocarbon density multiplied by the saturation of the hydrocarbon. Okay, if you have hydrocarbon, this one, it's usually applied when you have gas, because the difference between density of water and density of gas is different. But if you have oil, usually you can skip it. If you have water and oil, the effect is very, very minor, okay? Neutron log is the same. And here we are showing you the neutron reading from the tool. This one is the summation of all the neutron from all the properties. Here we are taking very simple linear approach, okay? For the neutron, if you are using Excel or calculator using this linear approach, if you are using software, we don't use linear because the neutron is affected by a lot of properties. But don't worry, the software is reading is the same equation plus a correction factor. So the neutron here is equal to the neutron coming from the water plus the neutron coming from the hydrocarbon plus the neutron coming from the shale, plus the neutron coming from the matrix, okay? If you assume everything is water, this one becomes the neutron coming from the water, which is the porosity. The V shale, we have it from the previous step. Remember that we calculated the V shale from the previous step. So when we plug the numbers, the only unknown, and this one is the reading from the waterline tool, and this is the neutron of the matrix. If it's limestone is 0, if it's quartz -3 or -4, the water is 1. The V shale, you take the value from the interval in front of the shale. And so the only thing unknown here is the porosity. You shuffle the equation around and it will give you the porosity value. For sonic, the sonic tool, it got advanced with time, okay? We started with single, after that dual. So the sonic tool is very simply, you have at the top, you have a source or transmitter or emitter of sound waves. So we send sound waves to the formation and we have multiple detectors, okay? So the first log, it has 2 detectors and 1 transmitter, okay? It detects the speed of the sound at R1 and the speed of the sound at detector 2 and calculate the difference. The difference is controlled purely by the matrix and how compact is the formation. For this picture here, you have 2 transmitter, 4 detector, sometimes you have 8, that's just making the tool more sophisticated and more accurate. But all of them work on the same basis. You transmit sound waves here, emitter, and you receive at the receptor, you receive the sound at time t1 and time t2, the difference in time that is controlled by how compact is the formation, okay? And how compact is related to the porosity of the formation. So if you have 100% sandstone, if you have pure sandstone, okay, that quartz, the delta T will be 55.5. If you have a pure limestone, is 47, dolomite is faster, and anhydrite is 50, and salt is 60. For water, is based on the salinity, but it's roughly around 190. For hydrocarbon, which is oil, lighter oil in Hasramal is around 215. For gas is higher. But you have the end point. Now, for sonic, people try to find a linear correlation with porosity. It's very tough, very difficult. But we have a couple methods. One of them is the linear I'm showing you here. So the sonic measurement, it's simply the summation of all the sonic from everything in the rock. The sonic from the water, the sonic from the hydrocarbon, plus the sonic from the V shale, plus the sonic from the matrix. If you assume at around the wellbore you have only water, all this term become the sonic from the porosity, plus the sonic from V shale, plus the sonic from the matrix. And if you look to the equation, the only unknown is porosity. So you can shuffle the equation around and calculate the porosity from sonic, and I will show you equation. You see the equation here. If you assume that the sonic from the water or the oil is the same, or you have 100% water, and you assume there is no shale, this is the simple linear equation of porosity from sonic. And again, it's similar to a single indicator, like porosity from density, like V shale from gamma ray. It's the same equation, it's just changing the physical measurement. So porosity is equal to the tool reading minus the matrix divided by the fluid reading minus the matrix. So in the industry, we don't use the linear. We have 2 equations. One is Wiley, which is the linear plus a compaction factor. Okay, for the equation looks very complex, but this is very simple. It's a linear plus this compaction factor. That's the Wiley and the Riemann-Hunt. The second one is not linear. And this is the from Riemann-Hunt. It's non-linear. Okay, the difference is very big. For the non-compacted rock, if you are very shallow, it's very big the difference. But if you are deep 30,000 meters or something, the difference is not that huge, in my opinion. But most of the people, they use the linear equation for simplicity, and because we are not relying on sonic only. Just to let you know, usually we don't run sonic by itself, always sonic with density at least. So you have the porosity from density and the porosity from sonic, and you can average both. I would give advice here, don't spend too much time to see which one is more accurate if you have a lot of sources. It's very quick and safer to average them to give you the best reading. But if you have one source, yes, at the time you can calibrate to rock data. So there is one big challenge if we have a gas in the formation. If you have a gas in the formation, when you look to your density, the density reading will be very, very low. You have a gas, okay? If you have this glass, half gas, when you calculate the weight, it will become very, very low. When the density is very, very low because of gas, and if you don't know it, you think you have very high porosity. That's why here we say the porosity is overestimated if you have gas. The neutron, if you remember what we said yesterday, the neutron, we are measuring how many hydrogen we have in the rock. The gas has less hydrogen in it compared to water. That's why the neutron reading will be very, very low. And if you don't know about it, you think you have a very tight reservoir. So the neutron will become very low, the density become very high. The beauty is if you have both of them, you can take the average and you will cancel the effect of the gas. The porosity from the density with the neutron average, you have the gas or you don't have the gas, it will give you a quite good porosity estimation. The sonic, unless you have very, very high portion of gas, the sonic is good. Unless 100% gas, that's when the sonic will be affected a little bit and show a higher porosity. But if it's a small proportion, don't worry about it. In the standard way, if you have this multiple sources, always average the porosity. So the final porosity is the average of all of them together, okay? So why we get the porosity from well logs, and we have another method. We have the core. If we have a core, carrot, we take the core to the lab and we can measure the density of density or the volume, and we can calculate porosity of the core. The problem for the cores are that the cost is very, very high. It's very expensive to take cores. It's very expensive to treat them and use them in the lab. Plus, the core, if they are drilling in loose sand like Canada, you don't have core, it's just loose sand, you cannot core it, you cannot have a core value, okay? That's why we go again and we say the petrophysics is the cheapest way to get information of the reservoir. The logs, they give you point by point everywhere, porosity, very cheap and very accurate. So always you pick few wells with core, and after that you run the entire reservoir with logs. And of course, when you do your porosity calculation, always you try to calibrate to this core. You start with well with core data, you do your interpretation, change the parameters till you have your porosity value is exactly or almost similar to the log, to the core value permeability, porosity, sorry. And that's the case here. You take few plugs here, few plugs here, few plugs of porosity. You calculate the porosity from the core, and after that you go and calculate the porosity from the logs, and you make sure that your porosity from the log at this point is similar to the porosity from the core at this point, and so on and so on and so on and so on. So you use the core porosity to calibrate your log porosity, and after that you calculate for the entire field using the logs only. There is, before we move, there is a total porosity and there is effective porosity, okay? The total porosity is the total pore volume divided by the bulk volume, porosity total, okay? The effective porosity, okay, is the interconnected pore space. We calculate only the interconnected pore space, but the definition is a little bit difficult and loose. In the domain of petrophysics, effective, it means corrected from V-shale. It means total minus the V-shale correction, Okay, because people, they define effective differently, but in petrophysics it's very simple. It's your total porosity minus the effect of the shale or minus the porosity that we see from the shale. That's effective. And always we work with effective, guys. There is one company that work with total is Shell. Else than that, 99% of the companies, they use total porosity for all their calculation. At the exception of Shell, they always use total, and all their workflow and equation is based on the total. So that's why sometimes you see the total in some literature and books. So if you take the calculation, is very simple. You have the same, I'm showing you the same example from yesterday. You have the gamma ray that give us the V shale. We have the neutron density that will give us the V shale and also give us the porosity. You do some calculation and it gives you your porosity. This porosity track, it shows you the red line is the effective porosity and the blue line is the total porosity. And you can see that in front of the shale, the total porosity here is almost 12–13%, but the effective is 0. Because that 12–13%, it's bound water to shale. And why we don't want it, we don't use it, because the bound water to shale, it cannot be moved at all at reservoir condition. So, and also it's attached to the shale and behave as one element, as one rock. That's why we don't use it in our calculation and we don't use it in our reserve and how much oil we have there, only effective properties. And that's, you see, if you have a clean sand, you see that total and effective are the same, okay? So if you have a shale interval, it's easy to pick and you can remove by yourself. You say, oh, this is a shale, I will not use it. When you go to very clean sand, you will see that both of them, they are equal. Now, where is the problem? The problem is where you have a little bit of shale, like here. When you have a little bit of shale, that's where is the problem. The total and the effective are not the same, and they may cause a problem for us. But if you have a clean sand, it's okay. They are the same. If you have a total shale, it's okay. We know that is total shale. We will not count it at all. After the porosity, we calculate the water saturation or how much hydrocarbon exists in the formation. So V shale, we use gamma ray SP or dual indicator neutron density. Porosity, we use density neutron sonic. And if you have all of them, you average it. Sometimes we average, we give more weight to density, but you can take it simple and average all the three and you get your final porosity before you go to water saturation calculation. What we mean by water saturation, we have the pore space, part of it is water, part of it is hydrocarbon, okay? And you will see why we always say in petrophysics water saturation, we don't say oil saturation, because simply the physics we are using see the water, okay? Here there is 3 examples of 3 rocks, okay? The first rock is very tight rock with very low porosity. The B and both here is B and B. This one is filled with water. This one is filled with hydrocarbon, okay? You see, if you calculate conductivity of this rock, you put 2 cathode and you calculate the electrical current that moves inside the rock, you see that this one will have very low conductivity because it doesn't have porosity a lot. This one, it has porosity filled with water, the conductivity will be low. This one, the pore is big but filled with oil, because the oil you cannot transmit electricity, the conductivity will be very, very low. Okay? From this, you can see that we are not seeing hydrocarbon, and we don't see, here we don't make difference between oil and rocks in resistivity or conductivity. We do always the difference between water and something else. So is it rock or is it oil? The resistivity tool and electrical tool, they don't see, they don't know. The electrical measurement measure how much water and how is it structured and connected together. That's why when we do our interpretation, we call it water saturation, because we see water, we see volume of water. We don't see the oil, we don't see the tight reservoir. You see a tight reservoir will have a very high resistivity, very low conductivity, and oil reservoir also will have a low conductivity. In oil industry, we prefer to use resistivity. Resistivity is very simple, is the reverse of the conductivity. And that gives us very quick interpretation when we look to logs. High resistivity mean oil, low resistivity means water. That the high is oil, the low is water. That's a simple equation. And after that, most of the work was done on resistivity, but that is the same. So if you take 3 cubes, okay, this cube is 100% water. There is nothing, there is no rock in it. Okay, so the saturation of the porosity is 100% and the saturation of water is 100%. And that you measure the resistivity, and that's what we call the water resistivity. So it's just put 2 cathode in water and you calculate the resistivity of the water. It's very easy and people, they do it in the field all the time. Now, if you take a rock of 20% porosity and you fill it 100% with the water and you calculate the resistivity, that we call it RO, or resistivity as 100% water. Now, if we take the same rock and you put 20% water and 80% oil, and you calculate the resistivity, that will give you RT, or the total resistivity. Of course, the total resistivity of the rock with oil is higher than the total resistivity of rock with water, and this one is higher than the resistivity of the water. I will not bother you with a lot of equation. I will just go and show you the most known equation for water saturation. We said that water saturation, if you have high resistivity, the water saturation is low. If you have low resistivity, the water saturation is high. And that's why this Archie equation, Archie is a gentleman that worked for Shell, developed the first saturation equation, I think 1941, for clean sand. For him, he was treating only very clean reservoirs. And he found this nice equation with a few components. You have the resistivity of the tool, or the total resistivity reading from the waterline operation, RT. And you have the RW, which is the resistivity of the water, as we explained previously. 100% water, what will be the resistivity? Porosity, how much porosity fraction in the rock? Those are the 3 values, and you have 3 parameters. Okay, this is a fitting parameter, empirical, and usually is equal to 1, the A. M is cementation factor and usually equal to 2. And N is saturation exponent and usually equal to 2. So in practical, A, we take it as 1, okay? M, we take it as 2, and we play with N. But A, N, and M, all the 3 components can be measured and estimated from cores. So when you work for any company, you go and look to your core report, you will find A, M, and N. Don't worry about it. And this is the water saturation. Other gentlemen, they came and modify Archie equation to accommodate for shale, to accommodate for the type of shale, is it laminated or dispersed? But the most dominant one is Cemento, or also the modified Cemento, and we have the dual water, okay? Cemento assume the shale is conductive differently than the water in the formation, okay? Dual water is simple, is assume you have 2 waters, the water in the pores and the water related to shale. And this one is the water in the pores conductivity is different than the water in the shale different. So the resistivity is different, and they assume there is 2 waters, okay? And this one is developed by Schlumberger, okay? And that's why you see this dual water exists in many books because Schlumberger, they advertise for it, and it's simple to understand. Dual water is simple to understand, simple to manipulate. That's why a lot of people use it directly. We have Indonesian, we have Nigerian, we have a lot. My advice is use the equation that people use for asset. For your asset, you are working for a company in a field. If the field is old, use your data. If your field is new, you need to do a very deep study which equation is better for your field. But if you don't know at all, use the dual water model. If you don't know, or for training purposes, use the dual water model. And the dual water, as we said, assume the water in the pores, resistivity is different and behave different than the water as bounded to shale, or the bound water. That's why they call it dual water, which is two type of water. There is another phenomena in resistivity. This one, let's say this is a helicopter view, top view. This is the wellbore, and the red is the mud cake on the wellbore. So when you put the mud in the wellbore, the mud will filtrate inside the formation, and it will push the oil or gas away, and it will be replaced by the water from the mud. Now, if you take resistivity in this zone, you will see your oil saturation is very low, and that you think your company is losing money. No. So don't use the resistivity in the very shallow area. Always, we try to go as far as we can where the rock is still intact, untouchable, or vierge. Okay? So here, the oil saturation is original, oil saturation. So always we take a resistivity tool that reads here. That's why for resistivity, always you have tools they read here, tools they read in the intermediate, tools they read in the far section. For water saturation, always we calculated using the deep resistivity. For the near, sometimes we calculate the saturation for the near wellbore to correct density and neutron, but that's not that important. The most important is SW, that we'll use to calculate our reserve and our resources, how much money we have. And always we use the deep resistivity. And this is just an example where you see always, you see the deep resistivity, you see the shallow and the micro resistivity tool reading, okay? And you can see that always we take the deep is the most accurate for our calculation, and that's very high resistivity. It means we have oil. This is low resistivity. It means we have water, okay? But we don't use the black to estimate our reserve. If we do so, we will make our reservoir all water. When we do your final interpretation, that's how it looks. There is a lot of things. كاين قدام من تراك 70,000 تراك 70,000 information. We don't worry. The most important are the last two. Okay. This one will tell you the porosity value as we showed before. And this one will tell you the oil saturation. You have oil in this section, and you have oil in hydrocarbon in this section, and hydrocarbon in this section. Okay. And that's the most important. All this is just intermediate calculation, porosity, V shale, R shale, blah, 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 blah. Don't worry about it. Okay. So that's how we calculate. Now, when we reach this step, we finish the petrophysical phase one interpretation. We have porosity, we have saturation, we have V shale, we have all of it. But before we deliver the report, our final report, we should deliver how much oil we have in this well. Okay. How much porosity we have, how thick, the thickness of this interval, the thickness of this interval, or the total thickness of oil, because the total thickness of oil will tell your boss how much we have. That's why this operation, we call it resource calculation or RESAM or resource estimation, summation, and depends on the software. Yeah, it's very simple. So you calculated the V shale, porosity, and water saturation using all the tools. Now, okay. You go and calculate the resources. The resources after we have V shale log, porosity log, and SW log, every company, they have a limit. They say if we have a porosity less than 5%, it's not good. The cutoff of porosity. They have some company, they have a cutoff of V shale. If V shale is more than 50%, don't take this interval as good, just drop it. So those, based on these cutoffs, we can calculate the net and the pay. Always, guys, calculate the net and the pay. And a lot of people, they don't understand the difference between the net and the pay. And the net and the pay, the difference is very simple, is like an English word. The net is the clean or proper in French, or nḍيف, okay, the interval nḍيف. What we mean by net is everywhere where we have very low shale and very high porosity. So the net has very good porosity and very low value of shale. That's why we call it net, because we refer to the volume of shale in it. If it's too shaly, that's dirty, we don't need it. That's the net. We don't care about if it's water or oil. First of all, that's the net. It's very thick, very big. After that, the pay, which is the money, the payment, that we add to it, we need to have a very good oil saturation or very low water saturation. So this is the net reservoir where we have all the movement. The pay is where we have our money. Okay. And based on that, you can calculate a lot of parameters. Okay. You can calculate what is the thickness, the total thickness of net, what is the total thickness of pay, what is the total, this one is the pore space. Porosity multiplied by thickness, that's the pore space, how much pore we have. That's a thickness. Okay. And hydrocarbon pore volume, porosity multiplied by thickness multiplied by saturation of oil, how much oil we have in a length, thickness of the well. So you see here from petrophysics, you get the information at the well, which is thickness now. If you multiply by an area, it will give you the volume. Okay. In Canada, for example, we drill every 400 meter. If you multiply by the area is 400 by 400, that's 1,600. Okay, that gives us usually 1 million barrel reserve. You can get your estimation using calculator, very simple. So if a well give you 1 in hydrocarbon pore volume, you multiply by your area and it tells you how much hydrocarbon you have around that well. Or you say, my well, it will drain 1 kilometer around. You can also calculate that area for you. But for petrophysicists, always we calculate thicknesses. And here on the same well, the green is all the interval, they succeed, then they pass, and they are net. You see the net, low gamma ray and good porosity. And it's all around the places. The red is the pay, is where we have good hydrocarbon. And you can see it's only at this top section and this top section. For example, if I take this section at 8,000, it's clean sand. Unfortunately, it's with water. So it's not pay. So that's the total interval. That's the pay interval. The net interval is the green and the pay is the red. And you have that one as a table, okay? Usually in every interpretation, we should show this table at the beginning, not even at the end. When you send email or report to your boss, always you report this one. You say that the total interval we drilled is 1,100 meter. The net pay thickness is 150, and the ratio is 13%. Porosity, average porosity of the pay is 21, and so on and so on and so on. So this is the most important. We look at it, and this number is the most important, which is hydrocarbon pore volume. Porosity multiplied by S, oil multiplied by H, and that's the most important number. Remember this number and remember the average porosity number that I will show you in a moment for something else. So now, when you do your interpretation, okay, you do volume calculation, you do a porosity calculation, you do a water saturation calculation, and to do volume shale, you need to have a gamma ray. Oops, let me just do it in one go. So for volume of shale, remember yesterday and today, you need gamma ray sand, gamma ray shale, how much the value. You need to know the neutron of the shale, the density of the shale, the sonic of the shale, all these parameters, you need to know about it, okay? And sometimes you are not sure. Sometimes the gamma ray shale, is it 150 or 140? The gamma ray of the sand, is it 20 or 25? So sometimes we don't know. The simple way I see is take your best guess. Let's say 20 is for the sand, do your interpretation. After that, when you finish, go back and run uncertainty analysis. And I will show you how to run it, okay? So uncertainty exists in all the parameters, and also uncertainty exists in the log, because the gamma ray reading itself, when it tells you have 75, for example, is it 75 or is it 74 or 76? So there is uncertainty in every work we do. That's why we always, when you finish, run uncertainty estimation, always. So uncertainty related to the log measurement, uncertainty related to your interpretation, all the parameters, density shale, sonic shale, gamma ray of the shale, density of the quartz, neutron of the quartz, all that. Plus the company cutoffs, because the company will tell you, we don't want to calculate anything below 10% porosity. But what if your boss say, oh, how about 9%? How about 8%? That's uncertainty also, we have to look at it, which one is controlling the final result. So how we do that, the Monte Carlo is very simple. You have all the interpretation is done and saved. So we say, I want to change the gamma ray of sand from 20 to 21 and keep all the parameters the same, do all the calculation and calculate how much reserve I have and save that value. Go back and change the gamma ray shale, for example. Go back, change the density of the water, and so on and so on and so on. For petrophysics, if it's single well, it's very quick. Usually we run around 2,000 to 4,000 runs. Each run, we pick the parameter randomly based on criteria. Let's say, for example, you can say that my quartz, the gamma ray is between 20 and 30. You check all the values. You will say, for example, the hydrocarbon density is between 0.7 to 0.8. You check all the values and you run the script, automatically run. I like interactive petrophysics because it's automatically is one click. You click and it will do it for you all and give you the result. Now, the result, you get an average value of all the 1,000 runs, and it gives you the standard deviation, how much is the uncertainty, and the tornado chart, which is the one I like the most. And I will tell you, run uncertainty, go directly to tornado chart, and that's the best way. So when you run, it gives you the red one, which is the average, and the yellow interval is one plus and minus one standard deviation. Okay, and you see this one is your porosity here. This one is your porosity. This one is V shale, and this one is saturation. Okay, porosity is 0 here. When the porosity is very low, don't worry about the uncertainty. Who cares? Porosity is 0. We don't care about certainty. Yeah. Okay. So don't waste your time looking to the uncertainty in front of zero porosity interval. Look to your reservoir. You see, this one is good porosity. Look to the uncertainty. What you can pick from here, if the yellow interval is thin, you are good. Don't worry about the number. You are good. If the yellow is big, like this one, you need to check why, because maybe you are wrong. So you need to check why. And that's why here we run the tornado chart. So in interactive petrophysics, run the 2,000, 5,000 run and directly go and generate your tornado chart. Tornado chart is very simple. Tornado will tell you which factor is affecting your data the most. كل بارامتر اللي راهو يأثر على البارامتر فينال تاعك البلوس. Okay. Here, for example, we are looking at an average reservoir property. One parameter, okay? As we showed you before, we have a lot. Average reservoir property. Which factor is affecting the most? Here is phi cutoff. Okay? Is the cutoff of the company is the one that control the average porosity. Okay? So can we change the company cutoff? Most of the time we cannot. It's not your job. It's the job of the entire company. So as a petrophysicist, you skip it. This factor I cannot play with. I will tell my boss that this factor is affecting the result, but if you don't want to change it, we skip it. Now, the second factor here is the gamma ray clay. Okay, you see that for porosity, a lot of people, they don't pay attention to the clay. They think in the reservoir, the most important factor is the density of the rock, the density of the fluid. No, it's not. And depends of the reservoir. And you see here, this one will take you roughly 5 minutes to run it, guys. Okay, so 5 minutes, you have a tornado chart that tells you if you want to adjust your porosity reservoir, your gamma ray clay is the factor that affects the most. So before you deliver your reservoir, your report, go back and check this value. Make sure you pick it correctly. Make sure you have a good number on it before you deliver your final result. This one is the density log. You see, the density log, which you get from Schlumberger, Baker, Halliburton, has more effect than the grain density. This is the density of the quartz, for example, here, which you can set 2.65, 2.64, okay? You see that this log measurement, uncertainty from it is more important than the density. So tornado chart will tell you exactly where to go, where to check. For me, I'll show you the second one, this one, okay, which is calculating the pore volume. Here is the hydrocarbon pore volume. Which factor affect the most? It's not like average porosity. This is the total. This is the resource. This is how much oil we have. The cutoff of porosity for this case is the most. Usually we cannot change this company criteria. The second one is M. The third one is RW, density, and so on and so on. Now, why I like the tornado chart? The tornado chart tells me the factor that affect my result the most. So, which means the factor that I can go and invest money to get it correct. tornado chart اللي تعطيك لي بارامتر كامل وشكون اللي ينفلونس لي ريزلت لو بلوس. اوتوماتيكمون الا حبيت عندك بروبليم شكون هو اللي تعطيكيه الاول. انا عندي هادو كامل دي بروبليم. عندي البوروزيتي تاع الارجيل، عندي الريزستيفيتي لوج، عندي هادو كامل الفاكتور A. Which one to start first to analyze and study and send to the laboratory, say, guys, I need you to give me better estimation of this. Tornado chart will tell you in 5 minutes. So M is the most important for you as petrophysicist. For this asset, other assets is different. So always I see as advice, run petrophysics from A to Z. Don't worry about too much the number details. Run a tornado chart uncertainty, and after that, pick which one affect the most, go back and try to get them correct. يعني كمل انت البيتاسو from كامل ومن بعد دير tornado chart وشوف شكون هما لي بارامتر اللي ينفلونسيو الريزلت البلوس، وهذوك لي بارامتر هما من بعد كونسونطري عليهم. قال انا غدوه ندير ايتيد على ام، نعاود ندير ايتيد على الريسيفيتي تاع الماء، نعاود نروح نبومبي ونشوف نهز دي شونتيون ونكالكيليه في اللابوراتوار ونشوفوا بيان. لا ما نروحش ندير ايتيد على كلش. دير ايتيد على كلش واحد ما يقبلك في الكومباني ويحاوزوك. اوكي don't ask your boss to do study on everything. You will be fired the second day. You as a professional, you need to be precise. Say, I need money to study factor 1, 2, and 3. The other, I don't care. It doesn't affect a lot. So always run in petrophysics from A to Z, run uncertainty, pick the parameter they have a problem or they affect the most, and go back and study them in details and enhance your interpretation. So like this, we finish the normal petrophysics interpretation. I will run very quickly on another application of the logs. The logs are used every day by the geologists to know what kind of rocks we have. Do I have a shale? Do I have sand? Do I have limestone? Do I have a very compact sand? Do I have a shale with a lot of water in it? Do I have compact shale? We use the logs because let's say we have 1,000 wells, 50 of them, they have core. We get core when geologists describe and see what is the lithology in every foot. Okay, عندنا لي كاروت، عندنا الليثولوجي تاع الكاروت، عندنا ارجيل جري ارجيلو انسو دو سويت. اوكي مي ال1000 بير الاخرين ما عنديش كاروت وحبيت نعرف لا روش تما سيكوا اوتوماتيكمون نيتيليزي اللوغ تاعي باش نكالكيلي. And here I want to show you one small step in machine learning, a small step in big data. Yeah. So this is a small application of big data, like Khalif was talking about it on Friday. We use the logs to estimate facies, and very simple. Okay. There is a lot of method. Okay, a lot of methods. There is a lot of blocks of methods. One block is the neural net, and below the neural net there is 1,000 of equations. Every university has their own neural net. Every company, they have their own neural net. Here is one of them, artificial neural net backpropagation. Is very simple. What this one is doing, the neural net here is as a physical meaning. Let's say X1 is a V-shape, okay? Let's say the output is the lithology, quartz, sand, and shale. If the gamma ray change, the change in gamma ray will change something in the middle, what we call the hidden layer, okay? And that something will tell me, is it shale or sand, okay? But as mathematically how we do the equations, so we say that X1, X2, X3, everyone has a weight, and we inject using the formula F to calculate the output. This F, every company, they have their own. The one you see here, reverse exponential, this one that exists in Petrel. Schlumberger exists in Petrel. It used to be in more than 20 years, the same equation. They use the same equation where they change the weights and they come up with the final result, okay? We'll give you, don't worry, so we'll give you an example, okay? Let's say we have one well where we have cores, okay? And the core tells me this interval is sand, this one shale is sand, this is silt, shale is sand, and this is shale, okay? That's what we call the training data set. I have the logs, I have gamma ray, neutron, density, and sonic, okay? Those are the most logs used for lithology, the gamma ray plus the porosity logs. What the system in the background is doing, okay, what the system is doing is very simple. It will take this facies, let's say you have 1, 2, 3, 4, 5 facies, it will split it into 5 inputs. It will go, for example, this one is the P3, which is the sand. In front of the sand, it will tell I have 100% probability of sand. Where I have other facies, it will be 0. Okay? And in the background, the system is not predicting sand and silt, is predicting probability for each one. So the system, you have 3 facies, the system in the background run 3 models. Model for the shale, model for the silt, and model for the sand. It will recalculate the probability. Here is 0 and 1, here is from 0 to 1. So that's one approach of the big data. After that, what the system will do, will go here for each depth. Let's say which one is the dominant. Here is sand, I will assign it sand. Here, which one is the biggest? Is this one is the shale, I will assign it shale. And so on and so on and so on. And you can see from few points from the core, we use the neural net and the big data and the wireline logs, we can predict facies everywhere in the well. And we can predict facies from this in other wells where we don't have core at all, okay? So before we deliver the model in big data, is not the model, is the hard one. The hard is how you fine tune and correct your model. Please do not click, click, click and run the model. No, try to understand, try to enhance it. One way to enhance the neural net is never feed the system with the information twice. What we mean by that, let's say you calculate porosity from density and you are using the density as input and you are using the porosity as input. So you are tricking the system. You are trying to trick the system. You are trying to tell the system the density twice, which is not good. So how we do it? In a lot of software, they show you the correlation between all the inputs. You see volume of shale, porosity, resistivity, porosity sandstone, which is neutron, this one, and density, okay, are the same here, and the correlation between each other. Of course, porosity with porosity, the correlation is 1. Now, the red one are correlation more than 80%. And you see that porosity, the correlation with V shale is 92, okay? So here, maybe it's better you try to discard one of them, okay? Especially if one is calculated from the other. If, let's say, for example, you have a good correlation between neutron resistivity, neutron density, and resistivity, you see 70%. This one, you can keep it Y, even the correlation is high, but physically is not the same. This one is electrical, this one is neutron. Okay, so if the correlation is very high, but the measurement is not the same, keep both inputs. But if the input is calculating from another input, please try to select one of them only. That's the first one. Don't feed the system with the information twice. Okay. Number two, you are using wireline logs. If those wireline logs, they cannot help you, why you use them? Okay. So if we take V-shale, the correlation with the total is around 50%, but the V-shale, it's giving me a good indicator of the shale facies, or this shale 0. Okay. We take another resistivity. So here, this example, all of them are good. Okay. So we see porosity, for example, it's very bad indicator for the calcite, but it's very good indicator for the sand. So I keep it, even it's not that high, but I will keep it. So make sure that this input, they can give you and help you for at least one element. If they don't help you in all of them, you are creating a noise, and that noise will make your neural net bad. Also, remember on the facies, we said that the system will say that the dominant facies will be taken as a final result. Sometime if you have 6, 7 facies, the dominant is around 21%. And say, no, we don't want to take 21 or 10. So our minimum probability should be, for example, 50 or 60%. And that also will make whatever you get here is the very high quality. In between, it will be interpolated later on in the 3D model. Also, the neural net will run thousands of runs for you. But most of the neural net now, they have a training data set. Training, whenever you run more, you get better model. But that's just overfitting. You have the cross-validation is the one that will help you. Cross-validation is a data set, is hidden. We go and check the model with. So most of the neural net, they will converge on this one. This one, I made it myself to look very ugly and very bad. But in reality, both of them, they should converge for the logs if you have good. This is one a real example. Both of them, they converge because my logs, they can predict my facies. Now, for this example from Canada, the facies was picked first on few wells using porosity and V-shale only. The geologists went to V-shale and calculate very block facies for few wells. We used this one to estimate everywhere. And one of the QC, you put the predicted versus the original side by side. You see, is it make sense or not for you, okay? Before you approve the model. Always build the model, QC it, and QC it, and QC it. Another QC is you look to the data spatially, okay? You have wells around, for example, this example, we picked one well here, one well here, one well here, and we look to our final result. Geologically, it makes sense or not. Here, don't worry about it as an engineer, it's the geologist's job. Geologically, this shale here is getting thicker here and getting thicker with something in between. Is it correct or not geologically? The geologist will tell you if is it acceptable or not. If not, he can do manual adjustment, manual correction. But that manual correction will be point here and there. But this neural net could be run in less than half a day, and you can predict your facies for thousands of wells. And that's what we call big data. Thousands of wells, that one is a lot of data to process. And it could be done thanks to all the big data algorithm and computer of powerful computers. Forgot about that one, that's an example, yeah? So with this, I will conclude my talk for today. And any question will be more than welcome. Malak?
Thank you so much, Mr. Khaled, for your amazing session. Mr. Khaled, let's wait for any questions.
Yeah.
Are there any questions? Don't be shy.
So waiting for the question is for petrophysics, always we take it simple. We calculate volume of shale first, followed by porosity, followed by water saturation. Okay, now, the sound is good or not, Malak? Malak?
Yes.
Okay, because I hear some noise. I showed you the basic of petrophysics yesterday and today. For people who love more advanced petrophysics, we don't take in petrophysics volume of shale, porosity, and SW. No, if we use software, we take everything together. We take all the box in one go. We calculate volume of shale, porosity, and SW all in one box in one go. And that one you cannot, unfortunately, you cannot do it in Excel or calculator, or you can do it only on software. Yeah, most of the software they have it. We call it multi-mineral analysis. Multi-mineral analysis, we take the entire box together. And also I showed you day-to-day petrophysics. We did not talk about sedimentology, petrophysics, or advanced logging. Advanced logging, we have, for example, the ECS or elemental core logging. That's a tool that measures the element for you. It will tell you how much aluminum, how much iron, how much magnesium, how much zinc, how much calcium you have. And from these, you can build your very complex model. And you can see on what I showed you this last 2 days, we have matrix, quartz or limestone, just matrix, one matrix. We have one shale, and we have two liquid, water and oil. That's it. So if you have more advanced logging, you can go to the matrix and you say, I have quartz, I have a little bit of anhydrite in it, and I have a little bit of calcite debris in it. And the shale, I have different shale 1, shale 2, shale 3, shale 4. And inside in the liquid, I have water, I have very heavy tar, and I have oil and a little bit of gas. But this, I did not touch it because it will take a long time. And believe me, it's very simple. If you understand the simple one, the advanced one will be very easy. So the simple one is V shale calculation, porosity calculation, and water saturation calculation. Any question, Malak?
No, Mr. Khaled, there is no questions.
So,
Thank you. Thank you so much, Mr. Khaled.
so Malak, sorry for the next couple session, we will focus on 3D geomodeling. And also we will do uncertainty. Yeah? I showed you uncertainty in petrophysics. I will show you uncertainty in 3D, because don't believe anyone, including myself, that tells you we know exactly. Okay, uncertainty is everywhere, and please, whenever you finish any interpretation, run uncertainty analysis on it. Anything, run uncertainty analysis. And that uncertainty analysis is the one that will save you and save your company. And we'll tell you, we try in your work, please don't say I have 25% porosity. Always say I have 24 to 26. Avoid this one number, always go an interval.
Yes.
Uncertainty will help you.
Yes, thank you so much.
And I am done for today.
Thank you, Mr. Khaled. Our participants, thank you for your attention. And I would like to remind you that the session is recorded and you can watch it next in our YouTube channel. Thank you and good night.
Good. Assalamu alaikum.
Wa alaikum salam.
Thank you, Khaled. Appreciate it.